I can't make the circuit simpler than this. Obviously, we're talking one of each element. They, though, can make the circuit way more complicated than this. And I don't mean complicated because it has lots of capacitors and lots of resistors. That's not what they're going to do. They're going to make a circuit that has transient nature. Perhaps a circuit that in one step with a set of switches charges the capacitor and then through another set of switches discharges the capacitor someplace else. You set up a circuit with a function. The simplest function I can probably throw out there is that most older cameras used to use a capacitor and a resistor for the flash on the camera. That's how they worked. If you buy a disposable camera from the drugstore, if they still make those things, and it comes with a flash, it uses a capacitor, a resistor, and a battery. Has anybody ever bought one of those before? So that noise you hear when you turn the flash on, believe it or not, that's the piezoelectric capacitor charging. It rattles and it makes this high-pitched whine as it charges. And when you discharge it, it fires all the charge through the resistor all at once. The resistor is the bulb. And then you have to wait for it to charge again. It's two separate circuits. It's a simple circuit to build. Now, you probably could already guess that the resistor probably does something to control how fast the capacitor charges. And I hope that you could put that together on your own because you know about Ohm's law, which suggests that the amount of charge that's moving through the circuit is being regulated by the resistance. So it should make some sense that the resistor serves a role in determining how long it will take for this capacitor to charge. But the capacitor isn't on its own here. We know that the amount of charge a capacitor can hold is dependent upon the size of the capacitance. So a capacitor that can hold more charge will also take longer to charge because it's going to take longer to get all those charges in place. I suspect that by the end of this discussion, we should see a clear indication where increasing the capacitance should make it take longer for the capacitor to charge. I think that's obvious. And increasing the resistance, which reduces the current, should also make it take longer for the capacitor to charge. I don't think that's an unreasonable prediction to make. Can you guys follow with the logic there? So we're going to try and come up with a function. I is a function of t that tells us how is it that this capacitor system charges. And I'm hoping that when we're done, how it charges makes perfect sense. But to get there, it's heavy in the math. It's not the heaviest math we've done, but it probably ranks right up there. If you were in mechanics last year, we did this problem. This problem shows up in nature in a lot of ways. The last time you might have seen this project in nature was when we talked about laminar drag, where the drag force was proportional to the velocity. The mathematics for that is the same as this. And for you guys who have never seen that, math is going to be kind of a challenge today. That's okay with me. So, close the switch. The switch closing is time equals 0. I'll remind you about our boundary conditions, and these problems will have boundary conditions. And the boundary condition is simple. At t equals 0, there's no current in the circuit. Well, let me not say it like that. Let me say it like this. There's no charge on the capacitor. Let's start with that. At t equals 0. And t equals 0 will be the moment the switch is closed. All right, that's when the timer begins. Everybody understand? All right, this is a Kirchhoff's law problem. So we want to generate a Kirchhoff's law equation. We're going to use the voltage equation because there's no breaks in the circuit, so I don't have to use the junction rule. I'm going to use the voltage rule, which tells me that when I go around my circuit, I'll have the voltage from the battery minus the voltage drop across the capacitor minus the voltage drop across the resistor has to equal 0. That's our starting form. Now, no big deal here. We've done a little bit of this before. Our job now is to start coming up with what we know to replace here for the voltage across the capacitor and the voltage across the resistor. The voltage drop across the capacitor is dependent upon the charge on the capacitor. So we solve this for V, and we get an expression for the voltage drop across the capacitor. Voltage drop across the resistor. Well, we solve Ohm's law for V, and we get our voltage drop across the resistor. Now, I made a mistake. It's small, but it's something I told you at the beginning, and I want to correct it. And that is I use lowercase variables to indicate things that change over time. And I want to continue that. Lowercase variables to indicate things that change over time. So I'm putting a lowercase q on the capacitor because I know at times 0 it's 0, but it's going to increase. And I put a lowercase I in for the current because I'm not sure what the current's going to be at time 0, but I have a suspicion that it's likely to change over time because at the steady state condition, we know there will be no current in this circuit because current can't pass the capacitor. Eventually the capacitor will be charged, and I don't think there'll be current in the circuit. Right? This still has to equal 0. Now, this is just applying Kirchhoff's law to a straightforward RC circuit. What you should be looking for in a problem is the following statement. Create a differential equation that could be used to solve for, and then there's 3 possible things here. You ready for them? The current as a function of time through the resistor or through the battery. That's one thing they could ask for. The current as a function of time through the resistor or through the battery. They could also ask for the charge on the capacitor as a function of time. And lastly, they could ask for the potential difference across the capacitor or across the resistor as a function of time. Those are the 3 possibilities of what they could ask about. They could ask about current, charge, or voltage. The 3 things we've been talking about the whole time when it comes to these circuits. But they want you to create a differential equation that could be used to solve for one of those 3. Now, if you recall earlier in the year, or if you recall last year, creating a differential equation means replacing a variable with its differential equivalent. Now, we haven't talked much about the differential equivalence of the things here in the circuit, but one of them is a clear differential. And if you don't remember what it is, I'll throw it out there. I is a differential. It's the flow of charged particles. It's the rate that charged particles pass a single point in the circuit, which means that I can be written as the differential of charge with respect to time. This is an important differential that I'm bringing up now. I didn't bring it up really before. I defined charge, but I never defined it as a differential. I'm sorry, current. I defined current, but I didn't bring it up as a differential. But current is the rate that charge passes through a circuit. So in this case, it's the rate that charge flows through the circuit, dq dt. So ignore the circuit for a minute, create my differential equation. Now, it cracks me up that you're going to get points for just doing this. But you will. Because remember, they're going to treat the mathematics of this a little separate from what you understand for physics. This is creating a differential equation. The next step will be to solve the differential equation. Now, by all rights, I made a bit of a huge overstatement a minute ago. I told you that there was 3 different things they could actually ask about. They could ask about the charge on the capacitor, the current through the resistor or battery, or the voltage on the capacitor or the resistor. The truth is, the only thing this differential equation can do is solve for charge as a function of time, which is what we're going to do. We're going to solve for charge as a function of time. That's all this function can do. But when we're done, I'm going to show you how it can be used to do the other 2 things. Does everybody understand? All right. Now, if you don't remember this from your prior work in mechanics, or if you've never done this before, we're going to use the process of splitting a differential. Now, if you remember it, great. If you don't, I'm going to go through the set of steps because most people require a refresher. If you're good at this, don't wait for me. You know how to do it. If you're good at it, take off and do it. But if you're not good at this, then I'm going to go through the series of steps. I'll highlight the steps because you will have to do this on your next test. So we're talking about next week. All right, you have to solve for the differential first. And there are a variety of different ways some people like to do this. I want you to get it all by itself completely. That is step one, get dq/dt by itself. I generally get it on the left side because I think more for me, the way I work, it works better there. But I move that side, I get v minus q over c. Now, you can actually leave the r in place, but I generally go ahead and divide both sides by r to have the dq/dt completely by itself. So all right, so step one, solve for dq/dt. Get it completely isolated.
Can you leave it in the, like, together, like v minus q divided by c over negative r? Does that work?
You mean combine this into a single fraction? Yeah, I don't care. There are advantages and disadvantages to both. There's no reason to worry about that yet. Okay? All right, step two. I'm going to do step two here, so it's all on the same screen for now, but you need to split your differential. This is a two-part process. Splitting a differential merely means multiplying by whatever is on the denominator of the differential. So in this case, it'll be dt. So you'll get dq on one side, and you'll have v minus r minus q over rc dt. But you can't stop here. You have to also, after you split your differential, you have to collect terms. All terms that have t have to be placed on this side, and all terms that have q have to be placed on this side. And you can't add or subtract to do that. It's going to be multiplying or dividing. I bring that up because you'll notice there is a q in the problem for sure, but the q is located right there. So you need to get this whole thing and bring it onto the other side. And there is no term with t in it, so this part that has t will be on the other side. I recommend you do this in the most efficient way possible, which is to get common denominators first, turn that into a fraction, and then multiply both sides by the inverse of that fraction. Does everybody understand that whole statement I just made? So I'm going to do that, but when we're talking about this step of separating the differential and collecting like terms, you need to be aware of what you have and what is the most efficient way to do what we're about to do. It's going to be different depending on what your system looks like. But for me, I want a common fraction here. So I'm going to go ahead and get common denominators. I'm going to combine that into a single fraction. And now I will multiply both sides by the inverse of that fraction so that q is on one side. Now, there's debate about whether this is the right way to do it or not. And for you guys who are experienced at doing this, it might be easier to have left RC on the other side. Again, for those of you who are experienced at doing this and know what's coming in the future, it might be easier to do that. I'm indifferent. It makes no difference mathematically. So because I'm trying to lay these kind of set of steps out there and be consistent, I'm going to continue on with this method. But if you know where this is going, you can do well to put TRC and leave it on the other side. It's not going to change anything. It's going to eventually be over there. But either way, your job, this is step 3. We have now split the differential and we have collected the terms so that the Q's appear on the side with dq and the T's appear on the side with dt. Any question before we move on to the next step? Now, all of that is the differential equations part. The next part is calculus. It's why you take calculus. We are fortunate that this is a straightforward integration. And I use the word straightforward here because it really is a straightforward integration. But for those of you who are actually going to move on into mathematics a little more, you'll find that the whole topic of differential equations is a fantastic approach to why calculus only works for a very limited number of these things. Most things in nature obey differential equations, and the mathematics behind it is definitely trying to find tricks to solving these problems. This problem is nice because really there's only one variable involved, q. T doesn't even seem to show up yet. That makes this a little bit easier. And also, we don't have any second or third variable in here that depends on q or t. Differential equations have to be able to handle way more complicated things. But everything on the left side is independent. And everything on the right side is independent. They are equal to each other, but they can be solved independently. Now, to solve them, you have to integrate both sides. We have to get rid of the differential by integrating both sides. That is the next step. I do this different than calculus. You'll remember me saying that last year. And the difference is not a huge deal. It's that you need to set your limits of integration here and not do this as an indefinite integral and set it later. Set your limits now. I think we did talk about this earlier this year. But when you set your limits here, I want you to be really clear. You already have boundary conditions. Just live up to them, right? We started at time 0 when the charge was 0. So my bottom boundary is going to be the charge at time 0. My bottom boundary on time is time 0. Now, this part was the part that confuses you guys a little bit. I don't care. We should be past it by now. Your top boundary is the function. So we're talking about the charge that exists sometime in the future. Q is going to be the function of t. And the right side is t. So we usually are given our starting boundary. We're not usually given the top boundary. Now, each side of this gets solved independently. And I can tell you what, the right side's a lot easier to solve than the left side, right? We're just taking the integral of 1 with respect to t. So you'll be reminded that that means that's t to the 0 power, because that's what 1 is. And we take the antiderivative using the polynomial rule, which will make this t to the 1 power divided by 1, evaluated from 0 to t. That side's easy. This side, not so much. Now, before I go on, I hear a lot of rumblings and whisperings. Get those out of the way before we go on to the next part. Is there anything I need to address? All right, if you pull this RC out, then you find that this is on your integral table. You could look it up. We're not going to. I want to teach you something new today. But this is on your integral table. So if you take your equation sheet out, you'll see it. It's not with Q, it's with X. But it's right there. We, on the other hand, are going to, we're going to learn something today. So to do so, I'm going to, how am I going to do this? I want to do it this way. I'm going to move that over to that side and deal with this on this side. And the first thing I'm going to point out is first thing I'm going to do is I'm going to pull out the RC. Yes, sir.
Why can't you pull out the VC?
Because it's not in both terms in the denominator. It would have to be in both terms for me to be able to factor it out in the denominator. Does that make sense?
Yeah, I guess.
I can't be satisfied with a yeah, I guess.
What do you mean by
To factor something from the bottom and take it outside the integral, it would have to have appeared in both of these terms. So I can pull it outside the parenthesis. Does that make sense now?
yeah.
Okay. All right. We're going to use a process here, and I need you to learn this process so that you can be successful at it. If you're in mechanics, you know this process. I don't think we've done this in here yet. We're going to use something called U substitution. And if you've not done any U substitution, you're about to learn. This is separate from what we're doing. This is a calculus thing. And it's not related directly to the RC circuit, but it comes up on our exam a lot. So we're going to do something called U substitution. Raise your hand if you've heard of this before. All right, for you guys who have not heard of it before, it's not hard. I'll be honest. We're just trying to find a way to make this look better. And I'll tell you exactly what we want it to look like. We want it to have less stuff in the denominator. The reason is very basic. The integral of 1 over u with respect to u is the natural log of u. That's a very well-known, very straightforward integral, and it's on the integral table. This isn't 1 over q. It's 1 over a constant minus q. U sub works in situations like this to try and make our integral look like something else. That's what U sub is about. So that's what we're going to try and do. We're going to try and make our integral look like this. And look, you guys who have never done this before, I promise you that this first time is going to just be mean and confusing and garbage and is hard. But then you're going to notice that every time we do it, it's exactly the same. So after a while, you'll either learn how to do it through memorization or you'll forcibly refuse to learn it. Some of you will battle this and will never get it. If that's you, good luck. I'm trying. So we want to do exactly what I started with at the beginning. I want to replace this function with something that is simpler to integrate. So I'm going to let u be equal to VC minus Q. By its very name, we're going to be doing substitution. So I am subbing in VC minus Q with a holder, a placeholder, u. But to make this work, I need to integrate with respect to u, not dq. So the next thing I need to do is come up with something I can replace dq with that will have du. So once I've made my substitution, you take the derivative of your new equation with respect to the old variable. I'm going to take the derivative with respect to q. Well, the derivative of a constant is 0. That part's easy. Minus, well, the derivative of q with respect to q is 1. That's pretty easy too.
It's not dq over dt.
No, because we're taking the derivative of q with respect to q. The entire function was VC minus q. So I guess what if I wanted to do this better and I wanted to be a better teacher, and you guys should expect better of your teachers, I should have done this. I'm taking the derivative of both sides and written it like that. It was u, so I took the derivative of the left side with respect to q, and I'm taking the derivative of the right side with respect to q. If I was a better teacher, I would have done that from the start to make it less confusing. And then I would distribute the derivative to each term. So I did skip some steps I should not have. Again, the derivative of VC as it is a constant with respect to Q is 0. It does not change as the charge changes. And the derivative of Q with respect to Q is just 1. So that's still the answer there, and this is still du dq. Now we just have to solve this for dq. I'm sorry, for dq. So du equals negative dq. So dq equals negative du. We're going to put this there. I'll put that here. Is that better? All right. Well, we did it. We now have something that we can replace in my function. Now, if I was doing the entire process correctly, I would also translate my limits of integration. I don't do it like that, but your math class will. So in your math class, you would also translate your limits. I do it a little different. So for those of you who have done this before in calc, you know you can do that. I'm not going to. I'm going to now do the integral as an indefinite integral and then substitute back in my original function. Folks, I don't want to be rude here. If you've not done this, I need you to really pay attention. If you have, I need you not to distract the others who have never done this before. Okay, please. You need to know the integral that you're trying to get here. I was trying to get this to look like the simple form of the inverse because I am aware that once I factor out this negative sign, that this integral has a known shape, and it is the natural log of u. That's what I'm trying to do with u substitution. Produce something to which I already know the antiderivative. And I know the antiderivative of 1 over u is a natural log. The whole goal is to make this look like something that we do know the antiderivative of. Once I've done that and have taken my integral, I immediately replace my function with my original function for u. So I'm out of space. All right. Now, the last step, like always, when we're done with our integration, is to plug in your limits. So for the left side, that's t minus 0. The right side, a little more finicky. The natural log of vc minus q, vc minus q minus the natural log of vc minus 0. So I've plugged in my limits. Wow, I'm going to run out of time, so I want to finish. We're almost there. We've done all the calculus, and we've done all the u sub, and we've done all the differential equations. You could say we're done. Just get rid of the zeros. But this is a function of t in terms of q, and we wanted the function of q in terms of t, so you now have to solve that for q. Now that's a lot of algebra. But you're good at algebra. You've been in algebra like 3 years in a row. You're in like algebra 4 now, right? So this is not fun algebra, but it is just algebra. Now I'm looking at the people who really need to hear this. You should know what to do now. But a lot of you don't. And don't give up. I told you, there's a 1 in 2 shot. You'll have to do this on the exam. So you got to solve this for Q. For those of you who don't know how to do it, the first thing I'm going to do is just get the RC over to the other side. And if you're waiting for me to do it, that's a foolish errand. You should be ahead of me. But you might not know what to do next. Take an active role here. It's important. We need to get Q by itself, and the only way we're going to do that is to get rid of the natural log. You're supposed to know rules about logarithms. The easiest one here is to remember that when you're subtracting logarithms, you can divide them. That's the easiest place to start. Now I can get rid of the natural log by raising both sides to a base of e.
I'll never do that.
I didn't think that was sexy, but way to go. This is sexy math.
I don't like that. Yeah.
Now, there's a couple other things that you need to do. You still need to get q by itself, but once I raise both sides to a base of e, the e and the natural log cancel out, and we're left with the function inside. Can drop the bars, which signify absolute value. A lot of different ways you can do this part. You can multiply both sides by VC. That'd be a way to do it. And then just isolate Q. That might be the way you like it best. So we'll do that. VC, e to the minus t over RC, equals VC minus Q. I'm going to get Q on one side. Now, one more thing, and you probably wouldn't think to do this, but factor out the VC. All right. This is the charging equation. There's a lot of things in this, and some of them you probably can figure out, and some of them you can't. It takes experience. But the first thing I want to point out is this. This is the size of the capacitor and the size of the applied potential difference. That has to be the total charge when the capacitor is fully charged. So the very first thing I will do is replace that with capital Q to remind us that that is going to be the amount of charge on the capacitor when it's fully charged. By factoring this out, it tells me that I'm going to get a value that's in coulombs because everything in here is a unitless quantity. Also, it has to fit my boundary condition. And if you remember what the boundary condition was, it said the charge in the capacitor was 0 at time equals 0. Let's check our boundary condition. You should always check your boundary condition immediately upon completing the problem. So I am going to say at t equals 0, what happens here? Well, at t equals 0, 1 minus e to the 0 power. E to the 0 power is 1. 1 minus 1, 0. So this is 0. So Q at time equals 0 equals 0. My boundary condition is in check, intact. Now, here's where you guys as scientists have to think a little bit more deeply about this. What is the shape of this function? Do you know what it looks like? We've talked about it before. You should know. A few of you do. How would you describe it? I want a special word. There's a word here. Yes, sir? Asymptotic. Asymptotic. This is an asymptotic relationship. If you don't know what that means, it means it approaches an asymptote. And not just any asymptote. As t goes to infinity, this term goes to 0. Right? That's e to the negative t. So as it goes to infinity, that term goes to 0. So our asymptote is at Q. Truth is, our capacitor never reaches full charge. It reaches a full charge at time equals infinity. But infinity is pretty short in physics. It's probably just a couple of seconds or milliseconds. Now, there's more to talk about here, but you have homework now. Listen closely, because if you don't do this by tomorrow, I will be mad for a change. I want you to find a function for the charge and a function for the voltage. And if you don't know how, I'm not asking much. I'm going to tell you what to do, but I'm seeing people put their stuff away already, and that's infuriating, because I know this is stuff that's tough. Current is equal to dq dt. suggesting that if you take the derivative of that function, you get an expression for the current.
Can I help you?
Is the bell supposed to have run?
Yeah.
All right, come in. Live by your timetable.
Here's the contact info for Ryan.